Okay, today's lesson is from Chapter 8, Section 1, and it's on the concept of geometric mean. The first thing we need to do is we need to talk about what is geometric mean. So when we talk about proportions, we talk about this idea of cross products. So if I give you a proportion, you know that you're going to multiply across the diagonals and you're going to set them equal to each other. We may or may not have discussed the vocabulary that goes along with that. The cross product that kind of goes down and to the right are called the extremes of the proportion. And then the cross product, those two numbers on the bottom left and the top right, those numbers are called the means. So when I say the means equal the extremes, all I'm saying is that the means would be x squared here, and the extremes would be ab. So just saying the products of those things are equal. So geometric mean is actually specifically identified here. In a traditional proportion, this would have like a C and a D here. But in geometric mean, all it says is that the means are the same number. That's all it is. So if the denominator of one fraction is denominator of one ratio is equivalent to the numerator of the next ratio, then that's talking about the idea of geometric mean. We can talk about it numerically. So I can just ask you to find the geometric mean between two numbers, or we can also discuss it in terms of some situations, and we'll get to that next. So if I want to know the geometric mean between 12 and 15, all I need to do is take 12 and 15 and put them in the place of A and B. So 12 over some number, which is the geometric mean, has to be equivalent to whatever that number is over 15. And we know to solve this that all we have to do is cross multiply. 12 times 15, that gives us 180 equals x squared. I square root both sides here, and I get that x equals the square root of 180, which I of course then simplify. That's 36 times 5. So x equals 6 times the square root of 5. So the geometric mean of 12 and 15 is 6 times the square root of 5 exactly. We could figure out the approximate decimal value, but you know us, we want exact values. So we're going to leave it as 6 times the square root of 5. What does this mean? Well, that means that the geometric mean is the positive square root of the product of the two numbers. So that's another way for me to define geometric mean in terms of in relationship to two numbers. How are we going to use it geometrically? First, we need to stop and think about this diagram here. This is theorem 8.1. Again, the number of the theorem doesn't really make a difference, but the idea matters here. The idea is we have some right triangle. Actually, let me see here. We have some right triangle. Pull this guy right here. All right, so I'm going to go back to just drawing it. We have some right triangle, ABC, and C is the right angle. C is always the right angle, just so you know. So this is C. Here's my right angle. Here's A and B. And I'm going to call this angle 1 tick mark, and I'm going to call this angle, 1 arc, and I'm going to call the other one 2 arcs, just so I can differentiate between them as I move forward. When I drew the altitude, I created 2 additional triangles. I created triangle ADC and I created triangle CDB. I'm going to try to draw all 3 of them in the same orientation so I can kind of look at what's going on with them. So here's my right angle, here's my 1 arc, here's my 2 arcs, and the small one, the same thing. I'll go back and put the labels on in just 1 second. 2 arcs, 1 arc. So in my medium-sized triangle, the 1 arc is A, the right angle is right here, and that's D, and then the 2 must be here. I guess that's third angle theorem in action. Right, if these two guys are congruent, then the third pair must also be. In my small triangle, the right angle is D, the 2 arcs is B, which means that the 1 arc must be right here, and that's C. So if I look at these three triangles, they all have three congruent angles. So that means that that's enough information for us to say that triangle ABC is similar to triangle ACD is similar to triangle CBD by angle-angle similarity. What's that mean? Well, you know what that means. They're similar, so that means their corresponding sides are proportional. And we're going to use that idea to talk about the geometric mean theorem. So you'll see that this diagram is very similar to the previous diagram. It's just a right triangle with an altitude. Please be careful. This is not an angle bisector, so this is not angle bisector theorem, which we saw in semester 1. This is the geometric mean theorem. If I draw an altitude from one vertex, I have two different things that can happen. So again, I'm not asking you to memorize words here. I'm just memorizing the idea. I have similarity. I'm going to go with that concept of marking my angles. Okay, so I know based off of these versus drawing the three triangles out. I'm going to see if I can handle doing this without drawing them out. I have x over h in the left-hand small triangle. So this is the side between the one arc and the right angle. So that would correspond to this side of the medium triangle. So this would correspond to h over. And the h of the small triangle is between the right angle and the two markings. That goes with this side here, which is y. So there is that geometric mean idea. These two quantities are the same. So I know that this is, I can say here that the altitude is the geometric mean between the two hypotenuse segments. So that's kind of one situation that we can see. Second situation that we can see has to do with this guy here. So now, in the first situation, I had the altitude. I had a number on the altitude. I knew the height of the triangle. I knew the height of the situation. In this example, I do not know the length of the altitude. I have the length of the three sides of the large triangle. I know how the hypotenuse of the big triangle got broken up into two smaller pieces. I know the lengths of the two legs. So I guess that you could say I could use Pythagorean theorem to figure out this altitude if I wanted to. I could, I don't need to, because I can use this given information to help me find additional information. So what I can say in terms of geometric mean here goes something like this. Okay, now let's see. I'm going to do again. I'm going to stick with the marking idea, right? Because it helps me to see that similarity concept, which is what we want here. So if I go, I'm just going to focus on the blue guys, and we'll do the green guys. There's actually two situations going on here. In the blue guys, I can say that the short leg of the small triangle over the hypotenuse of the small triangle, so that would be x, short leg of the small triangle over hypotenuse of the small triangle, that would be equivalent to short over hypotenuse. So now I want to go to the short leg of the big triangle, triangle ABC, so that's B, over the hypotenuse over of the big triangle, which is C. So this is short leg over hypotenuse is what I did for the little triangle and for the big triangle. So there's that geometric mean idea. And I could do something similar with the greens. On the greens, again, I'm going to focus over here. So now I can go the long leg of the medium triangle over its hypotenuse equals the long leg of the big triangle over the hypotenuse of the big triangle. So this is long leg over hypotenuse for each of my ratios. So that's how I know they're corresponding. So when I look here, there's my geometric mean, there's my geometric mean. So I could say something like, let's see, shorten this guy up. I can say something along the lines of this. I can say the length of the leg of the large triangle is the geometric mean between the entire hypotenuse and the adjacent hypotenuse segment. So the leg of the large triangle is the geometric mean between the entire hypotenuse and the adjacent hypotenuse segment. Again, what do I mean when I'm talking about that? We know what we mean by leg. The entire hypotenuse, we're talking about C. Ooh, that's terrible. Let me switch my writing tool there. So the entire hypotenuse is C. And the adjacent hypotenuse segment, so if I'm talking about the leg B, then the adjacent hypotenuse segment will be talking about X, the piece of the hypotenuse that is attached to B. Okay? So that's the geometric mean theorem in action. Here we go. All right, solve for X, Y, and Z. So again, I see a right triangle, I see an altitude. I'm going to go for Z right off the bat because this reminds me of the idea that we just did here. We said that the altitude is a geometric mean between the two segments of the hypotenuse. So to solve for Z, I'm going to go right ahead and I am going to say that 8 over Z equals Z over 25, and I'm going to go from there. So I get Z squared equals 400. I believe the square root of 400 is 20, and we know that it's the positive square root, so Z is 20. From here you have options. You can keep going with the idea of geometric mean, or once you take notes and prove Pythagorean theorem, you can now go Pythagorean theorem. We haven't discussed Pythagorean theorem in class. We've been using it an awful lot, but we haven't actually proven it yet. So I'm going to continue with the idea of geometric mean. The next idea that I see is the idea of the legs. So if I move on to the legs, we said that the leg of a right triangle is the geometric mean between the length of the entire hypotenuse, which in this case is 8 plus 25, which is 33. So it's a geometric mean between the entire hypotenuse and the adjacent segment. Adjacent to y is 25. 33 times 25, well, I guess it doesn't really matter because I'm going to want to break it down in a second anyways. So it's the square root of 25 times 33. So y equals 5 times the square root of 33, leave it exact. And then I can do a similar thing for x. I can say that the leg is the geometric mean, and this is exactly how I would do my setup. I would write those x's in first, between the entire hypotenuse and the adjacent hypotenuse segment. So x equals the square root of 8 times 33. This is 3 and 11. This is 2 and 4. So x equals 2 times the square root of 66. And those are my exact values. Again, you could get those using Pythagorean theorem as well, but that's how you would use geometric mean in this sort of situation. Last up will be an application question. How can we use this? So let's just read through and I'll kind of tell you what's happening. And again, pardon my drawings, not my strong point at all, but you'll see what I mean. Community center wants to estimate the cost of installing a rock wall. So we have some rock wall. We'll pretend that's my rock wall. Okay. Sue holds a book up to her eyes. So here's Sue, right? And she has some book that she's holding up to her eye. That's her beautiful eye right there. So that the bottom and top of the wall are in line with the bottom edge and binding of the cover. So she's holding her book so that it lines up here and here. Now I need to make an adjustment because it's a book, so it needs to have a binding that is square. So my diagram is not particularly good. We'll just have to pretend that it is. Okay, so we know that Sue, the problem is I don't have Sue drawn in proportion to the wall. So we're just going to have to kind of pretend that is correct, but this is the general idea. So the book is right here, and it has a right angle in the corner. I'm actually going to erase the wall and the ground here because it is making this seem confusing. So let me see if I can fix this. So the diagram looks better for you. I want to make this longer, so it is a right angle. Actually, no, that's fine, whatever. We'll go there, and I'm going to make this longer again. So pretend it looks something like that. I'm sure it's actually the other way around because Sue's going to be like super tall the way I have her drawn, but that's the gist of it. Okay, so her eye level is 5 feet above the ground. So we are saying that here to the ground, which is down here, is 5 feet. And she's standing 11 feet away from the wall. Clearly this is not drawn to scale, but I already have recognized that that's a problem. She's 11 feet away from the wall. This is a right angle. This is a right angle. How high is the wall? So the overall height of the wall, the thing that they're looking for is this entire length here, which is the hypotenuse of the large triangle. When I look at this, what I see is that if I know what this is, then I have the length of the entire wall. So this looks like it's the altitude is the geometric mean between the two segments. So I'm going to just go ahead and set up my proportion where the altitude 11 is the geometric mean between the two segments. So I get that 5x equals, I believe this is 121. So x is whatever 121 over 5 is. That does not reduce, I do not believe. Let me just double check. I don't know why I'm checking. I know it doesn't reduce. So x is 121.5. And if I do that out, that comes out to be 24.2. I'm going to the decimal because this is an application question. So the wall itself equals the 5 feet from the ground to Sue's eyes plus the 24.2 feet, which represents the second segment. So our wall will be 29.2 feet high. Again, geometric mean application. Hope that's helpful. See you next time. Percy, my love, you may not be on the table. Thank you.